Before we can begin solving partial differential equations, we will need to discuss what the Fourier series is, which is defined as f of t equals a naught plus the sum from n equal 1 to infinity of a sub n cosine of n pi t over big T plus b sub n sine of n pi t over big T, where a naught, a sub n, and b sub n are Fourier coefficients. Fourier series. Now, these guys, apparently, they are the solution to many partial differential equations, which is why it's so important to solve these. So, to visualize what is going on, you will take a look at the square wave from an interval from negative pi to pi. Our function will be negative 1 when t is from negative pi to 0, and 1 when t is from 0 to pi. The periodic extension of f turns out to be f of t equals 4 over pi, sum from n equal 1 to infinity of 1 over 2n minus 1 sine of 2n minus 1 of t. Now the math to get here does not matter, but what it's trying to do is what we care about right now. Analyzing our periodic extension of f, if we increase the number of terms to capital N, we could see that the Fourier series is recreating the square wave. This is the main idea of the Fourier series and what it's trying to accomplish. You are adding a bunch of sine and cosine waves to mimic and approximate periodic functions. One insight is that we could see overshoot at discontinuities at x equals 0 and x equals plus minus pi. This is known as Gibbs phenomenon. We will now be discussing orthogonality. If we have two functions f of t and g of t, they will be orthogonal if the integral from a to b of f of t g of t dt equals 0. This is what is meant by orthogonality. As an example, let's take a look if sine of n pi t over big T and sine of m pi t over big T are orthogonal functions. N and m are going to be natural numbers, and we will check it over the interval from 0 to capital T. So we take the integral from 0 to big T of sine of n pi t over big T times sine of m pi t over big T dt. You can verify this using integration techniques, and it turns out it will be 0 when n does not equal m, and t over 2 when n equals m. This is known as an orthogonality relation. This concept is used to derive all of the coefficients in a Fourier series. We now turn away from the concept of orthogonality, and we will now be discussing the convergence of Fourier series. Given that f is piecewise continuous on a to b, the function f and its derivative f prime are continuous except at infinitely many points a to b, and all left and right hand limits exist for a to b. The theorem is if f is piecewise smooth on the interval negative t to t, the Fourier series will converge when the periodic extension of f is continuous and when the average of two one-sided limits from the left and the right at a jump discontinuity x equals a exists. So what does this mean? Well, the Fourier series will converge everywhere, and similarly, for jump discontinuities x equals a, it will converge to the midpoint. The midpoint is the average of the left and the right hand limits. This is the convergence of Fourier series. Now let's briefly summarize what we have learned from Fourier series. We now know that they are used to approximate functions using a sum of sine and cosine waves. We have also learned that orthogonality can be used to derive the Fourier coefficients of a Fourier series. And finally, Fourier series converge everywhere and at the midpoint for discontinuities. I hope this was helpful.